We're going to start today with something called slope fields. Now, even if we cannot solve a differential equation, we can still figure out what the graph of the solution of the differential equation is going to look like using slope fields. That means that even if we cannot find the antiderivative of a derivative, we can still figure out what the function looks like. Now, here's the way you do it. I picked out an example here where we actually could solve this differential equation, okay? But if we use that as our f, as our equation, and we make an xy chart, and we pick different x coordinates, notice that the y coordinate doesn't actually matter, does it, in this particular example. So whenever the x coordinate's -3, the derivative equals -2. So look what I did over here. I came to where all the x coordinates equaled -3, and I drew slopes of -2 because derivative is slope, right? And then I figured out that when x equals -2, the derivative equals -1, and I made all those slopes, and so forth. So having those slopes means I can now draw a sketch of a solution of this differential equation, even though I don't know what the solution is. Okay? So I would start off with the steep slope. It flattens out, goes to a slope of 0, starts going back up there, and that's a graph of a solution. And then, of course, I can get more of them. Oh, okay? Get the idea? And look, these can become very complicated. If you look at number 3 here, our derivative has an x and a y in it. So now, instead of a whole column of where all the x's are the same, the slope's always the same, I got to go by ordered pairs. At the ordered pair -3, -2, the derivative is -5. So at -3, -2, I made a really steep slope down here. And so see what I've done? All of this is to figure out slopes at different ordered pairs for that differential equation. And look, the solution is going to be complicated looking, isn't it? Okay, so it might be something like that, and on the other side, looks like there might be a slant asymptote there, doesn't it? For something down here. It looks like, in fact, it's probably not a function, but a family of functions. You know, like a circle is a family of functions. It's the top half and the bottom half. Looks like something like that's going on. All right? Or like number 6 here. Look how cool this is. And this one, we really can't find that antiderivative, can we? We don't know how to do that. Okay? But I can make a slope field which looks something like that, and then I can try to figure out, well, look, to be honest, that slope field's not quite big enough for me to get a good idea, is it? It probably needs to be at least twice that big for me to get a really good idea. But what I hope you're realizing is, by using slope fields, because there are times where we know a derivative and we can't figure out the function. There are times when it's easier to measure the rate of change of something than it is to measure the something. Like moving objects. It's easier to measure the velocity of an object a lot of times, like a car driving down the road, than it is to come up with a coordinate grid and measure its position at different times. Okay? So by knowing velocity, which is derivative at different times, we can figure out what the position function would look like. So slope fields are really handy. There's something that, there are things that certain types of engineers or NASA people or whatever, I don't know, might use from time to time because they'll know the derivative of something and they don't know what the antiderivative is. Now, those guys can figure out all the antiderivatives, okay? But they may not need to know what the antiderivative is. They may just need to know what it looks like. And you can go in. It's not rocket surgery. All right. So, this discussion leads us to number 70 on page 257. No, that's not number 70. What number is that? Is that 49? All right, 51 on page 256. So they tell us a differential equation, a point, and a slope field are given. A slope field, sometimes called a direction field, consists of line segments with slopes given by the differential equation. And we just looked at how you come up with those. These line segments give a visual perspective of the slopes of the solutions of the differential equation. So they want us to sketch two approximate solutions of the differential equation on the slope field, one of which needs to pass through the indicated point. Then they want us to use integration to find the particular solution of the differential equation. And then, if you find the particular solution and you graph it, it should look, well, your sketch you made should look something like the graph of the actual solution. Okay? Will they be identical? Not likely. All right, so here's what we do. First, let's try to sketch a couple of solutions. So our derivative equals the cosine of x, but fortunately for us, we don't have to come up with the slope field ourselves. They've already done that for us. All right, so let's try to use it to figure out what a solution might look like. So in here, I know you can't imitate this on your paper. I don't want you to draw 5,000 little slopes on there and then fit it on there, okay? So when you get to this in the homework, if you've got a copy machine available, fine. If not, just do your best. And maybe you can put a piece of paper over it and trace. I don't know. But try to figure out what's going to be going on. All right. So let's see. Let's try something like about this. Here, gets a little steeper, gets steeper, flattens out, goes up the other way, gets steeper, flattens out, goes back down the other way. Something like that. Okay? So, oh, come on, let me capture the whole thing. Anyway, then we can draw more of them, can't we? And there we are. Now, they wanted us to draw one through that point there. When you have to go through a certain point, you need to start at that point and then go to the right and go to the left. Otherwise, you know, you may not hit it like you wanted to. So if I start here, something like that. I didn't mean to do that. And there we go. So, why do we have more than one solution? Because if we take the antiderivative of that, we're going to get a plus c. So the c's are different for each of those three graphs, aren't they? Now, what are those graphs of? Those are graphs of the solution to that differential equation. Do we know the solution yet? No. But we do know what the graph of the solution looks like. Okay. All right, so now let's actually find the particular solution. So, in your notes, let's work this out. So we're given that dy dx, which is a derivative, equals the cosine of x, and we're also given that our function goes through the point 0, 4. So the rate of change of the function equals the cosine of x, and we're going to figure out what the function is, what the solution to this differential equation is. So start off, multiply both sides by dx. Take the indefinite integral of both sides. So I've got the integral of dy equals the integral of the cosine of x dx. Now, on the left, that's the integral of 1 dy. Well, since the variable of integration is a y, the integral, the antiderivative of 1 is not x, it's y. And on the right side, and you may have to look this one up, but the antiderivative of the cosine of x dx is the sine of x plus c. Makes sense, doesn't it? Because what's the derivative of sine? Cosine. So the antiderivative of cosine should be sine plus c. All right, so that's our general solution. If they did not tell us that our function goes through the point 0,4, that's as far as we could go, isn't it? Okay, so that's our general solution. But now we get to find the particular solution because they give us an initial condition. All right, the initial condition is that whenever x equals 0, y equals 4. So at the point 0,4, replace x with 0 and replace y with 4. Well, what is the sine of 0? 0, so 4 equals c. So our particular solution is y equals the sine of x plus 4. Which of these graphs, the black one, the red one, or the blue one, is the graph of that particular solution? The blue one. All right? The other graphs have different c's. Uh-huh. Mm-hmm. Not really. All right. We good? Okay. I kind of like slope fields. All right, number 54. This time, the directions tell us did I copy the wrong directions on there? No, that's the same direction. Use a graphing utility to graph the slope field for the differential equation. Use integration and the given point to find the particular solution. And graph the solution and the slope field in the same viewing window. I don't know how to make a slope field on my graphing utility. I don't think it does that. Maybe yours does. I don't know. Go home and find out. All right? So here's the way I'm going to do 54. We're given that dy dx equals 2 times the square root of x, and then our initial condition is that the point 412 is on our graph. Well, we can solve this, so let's solve this. Multiply both sides by dx, and at the same time, I'm going to change that square root of x to an x to the 1/2. Take the integral, the indefinite integral of both sides. The integral of 1 dy, the antiderivative of 1, since the variable is y. And then use the power rule for anti-differentiation. Add 1 to your exponent, make that an x to the 3/2. Then divide your coefficient by 3/2. Our coefficient is 2. Dividing it by 3/2 is the same thing as multiplying it by 2/3. So we get 4/3 plus c. That is our general solution of this differential equation. To get the particular solution, use the fact that whenever x equals 4, y equals 12. So at the point 4, 12, replace x with 4 and y with 12. So that becomes 12 equals 4 thirds times 4 to the 3 halves plus c. Now that 4 to the 3 halves, that means the square root of 4 cubed. Square root of 4 is 2. 2 cubed is 8. So that's 32 thirds plus c on the right. Now we need to subtract 32 thirds from both sides. Now 12, isn't 12 the same thing as 36 thirds? So 36 thirds minus 32 thirds is 4 thirds. So y equals 4 thirds x to the 3 halves plus 4 thirds. And that is the particular solution of that differential equation that goes through the point 4, 12. All right, so now we need to figure out what the slope field looks like. Now, I started with this. I'm not going to use that. So draw your little XY plane. And draw your little x, dy, dx chart. That way. All right, so let's start figuring out some slopes. Our derivative doesn't have a y in it. So that means that whenever x equals, in our first case, 0, the slope is always going to be, because the 2 times the square root of x, the slope is always going to be 2 times the square root of 0. Well, 2 times 0 is 0. So whenever x equals 0, the slope is always 0. So put a bunch of little zeros, slopes of 0. All right, then when x equals 1, the slope, the derivative, the slope, will be 2 times the square root of 1. Well, 2 times 1 is 2. And then, look, you just got to estimate, don't you? Okay? So I estimated when x equals 1, these slopes of 2. And then it starts getting nasty. Because when x equals 2, all the slopes are going to be 2 times the square root of 2, which is a little bit less than 3. So I wanted them a little bit steeper. And then you can see what I did for the rest of them. And look, you're just estimating. Estimating is the best you can do here. Now, is anybody surprised that I didn't bother putting any negative x's into the chart? Yeah, negative x under a square root doesn't mean anything to us, does it? Okay? And since that's the case, and since we always do it with the principal square root, everything ended up being in quadrant 1, didn't it? And then you do your best to fit in a couple of graphs of solutions. Starts off flat, gets steeper. Starts off flat, gets steeper. Starts off flat, gets steeper. All right? What do you think? And seriously, if you've got a relatively new calculator, go home and see if it does slope fields. I'm sure most of them do, since the book expected you to have one that does. Maybe mine does. I don't know. I'm not sure slope fields had been invented when TI-83s were made. None of them do? Huh.
Well,
All right, number 68. All right, on number 68, it says use acceleration equals negative 32 feet per second per second. Quite often you see that as feet per second squared, as the acceleration due to gravity. We're going to neglect air resistance, which is very convenient. For 68, we're going to show that the height above the ground of an object thrown up from a point S0 feet above the ground with an initial velocity of V0 feet per second is given by the function f of t equals negative 16t squared plus V0t plus S0. We're supposed to start with that. So we're given that the acceleration function with respect to time, so a of t, acceleration is a function of time, is negative 32 feet per second squared. Now, remember how it works? You start with the position function, take the derivative, that's velocity, take the derivative of that, it's acceleration, go backwards. If we start with acceleration and we take the antiderivative, what will we find? The velocity. So, the antiderivative of negative 32 is the velocity function. So v of t equals the antiderivative of negative 32. Now, on most of our integrals, we've been throwing in a dx. How come this one's a dt? Yeah, it's a function of time. So the velocity function is the antiderivative of acceleration function, or the velocity function is the indefinite integral of negative 32 dt. Well, we can do that. What's the antiderivative of negative 32? Negative 32x, but not x, t, so negative 32t plus c. And I'm calling that c1 because I'm going to have to get to the position function, I'm going to have to take an antiderivative again, right? I'll have a different c then. So I'll call that one c1. Now, they tell us that the initial velocity is called v0. Initial velocity means the velocity at time 0. Okay? So when time equals 0, whatever the velocity is, that's the initial velocity. So when time equals 0, our initial velocity isn't a number, it's v0. So, velocity at time 0, v of 0, that's the velocity at time 0, equals v0. Okay? All right, now, at time 0, we can put a 0 in for that, right? Okay? So, v0, maybe I should have even done this. Maybe I should have v of 0, which is called v0, equals, and then put in a 0 for t. Negative 32 times 0 plus c1. And what is negative 32 times 0? So our initial velocity is simply whatever c1 is. So this is kind of weird. When we call something a particular solution, we expect to only have the t in this case, or x in many cases, and everything else is a number. Well, we still have the t, but C1, instead of writing C1, what are we now going to write? V0. So the particular solution for the initial condition that the initial velocity is V0 is V of t equals negative 32t plus V0. So, as awkward as that looks, that is the particular solution with the given information they have. And guess what we do now to find the position function? We do it all again. All right, so the position function, s of t, is going to be the antiderivative of the velocity function. It's going to be the indefinite integral of the velocity function. Notice again, at the end of that integral, it's a dt, because our variable is t, it's a function of time. What's the antiderivative of negative 32t? It's negative 16t squared. Add 1 to the exponent, that makes it a 2. Divide your coefficient by the new exponent. Negative 32 divided by 2 is negative 16. And what's the antiderivative of V0? Remember, V0 is a constant. So it's V0t. Just like the antiderivative of 5 would be 5t. So the antiderivative of V0 is t. Plus c. So I call this one C2. So the general solution for our position function, what's our initial position? What do they call it? S0. So when t equals 0, the position is S0. So again, I probably should have written S of 0 equals S0, which equals, well, go back to your general solution and put zeros in for t. So what does C2 equal? S0. So for our particular solution, replace C2 with S0. Now, they said that what we were going to do is that we were going to show that the height above the ground of an object thrown with those conditions they gave us, we're going to show that that would give us the height. Is that what we came up with? Yeah, the only thing we called it S, because we had always called position S. For this problem, what do we need to call it? F. That was fun. Question? All right, number 70. A balloon. Oh, use A of t equals negative 32 feet per second squared again. A balloon rising vertically, velocity of 16 feet per second, releases a bag at the instant it is 64 feet above the ground. How many seconds after its release will the bag strike the ground? And at what velocity will it hit the ground? All right, so I probably should have written that we're given A of t equals negative 32 feet per second squared. We're given what the initial velocity is, okay? Because the balloon's going up with a velocity of 16 feet per second. So when the sandbag is released, it's going up at 16 feet per second, isn't it? So it's not an initial velocity of 0, because when the sandbag is dropped, it's already going up with a velocity of 16 feet per second. So the initial velocity is 16 feet per second. What's the initial position of the sandbag? 64. Notice that with initial, we're not starting when the balloon's on the ground, are we? We're starting when the action starts. The action starts when they release the sandbag. And when they release the sandbag, its velocity is 16 feet per second, and its position is 64 feet above the ground. So the initial velocity is 16 feet per second. The initial position is 64 feet. Now, we just got through proving in number 68 that whenever that's the acceleration, that the position function is, and what did we say it was? It was negative 32t plus v0t plus s0, wasn't it? We just got through proving it in number 68. Do you think it's fair to use that again? Yeah, it is. So the initial, or the position function is, oh, wait a minute, what negative 32? It was negative 16t squared. That was a close one. So it's negative 16t squared plus v0t. What's the initial velocity for this problem? So that's your v0t, 16t, plus s0, the initial position. So plus, then the initial position for this one is 64. All right. So now we have the position function. First question, how many seconds after its release will the bag strike the ground? How high off the ground is the bag when it strikes the ground? No high. It's 0, right? It's 0 feet off the ground when it hits the ground. So we need to know when the position equals 0. So the sandbag hits the, when the position, S of t equals negative 16t squared plus 16t plus 64 equals 0. And the reason that's the correct equation to use is because when it hits the ground, it's 0 feet off the ground. Its position is 0. All right, we can solve that. Let's figure a negative 16 out of that. And then when you divide both sides, negative 16, we get t squared minus t minus 4 equals 0, don't we? And I really wish that was factorable, but guess what? It's not. So we use the quadratic formula. So t equals negative b plus or minus the square root of b squared minus 4ac over 2a. So a is the coefficient of t squared, so it's 1. B is the coefficient of t, so it's negative 1. And c is the constant, so it's negative 4. So negative b means negative of negative 1 plus or minus square root of b squared, negative 1 squared, minus 4ac, so minus 4 times a, which is 1, times c, which is negative 4, all that divided by 2a. So 2 times 1. So underneath our square root sign, I get a positive 1 and a positive 16. When I add those, I get 17. Now, I've got that plus or minus sign. Square root of 17 is a little bit bigger than 4, right? Since square root of 16 is 4, square root of 17 is a little bit bigger than 4. Well, 1 minus something a little bit bigger than 4 is negative. Does negative time make any sense for this problem? No. So get rid of the minus on the plus or minus. And that's the time when it hits the ground. So something a little bit bigger than 4 plus 1 will be something a little bit bigger than 5. Divided by 2 will be a little bit bigger than 2.5. So in a little over 2.5 seconds, it hits the ground. It's 2 point what? 2.56, blah, 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 right? Okay, so that's when it hits the ground. At what velocity will it hit the ground? Okay, now, we never did find the velocity, did we? Let's find the velocity. If a of t is negative 32, the velocity is going to be the integral of that. So the velocity is going to be wait a minute, I'm confused myself. So yeah, negative 32t plus c, okay? And when t equals 0, that'll be negative, well, when t equals 0, v of 0 equals 16, right? So we can make that negative 32 times 0 plus c1, and that's got to equal 16. So 16 equals c1. So our velocity function is negative 32t plus 16. You follow me on all that? Questions on any of that? Exactly. So the velocity when it hits the ground is the velocity at 1 plus the square root of 17 divided by 2. So v of 1 plus the square root of 17 divided by 2 is negative 32 times 1 plus square root of 17 divided by 2 plus 16. All right, so let's see, I can divide that with that, make that a negative 16. So negative 16 times 1 is negative 16. Negative 16 times square root of 17 is that, plus 16. And notice I did want to do it that way because I've got a negative 16 and a positive 16. So I can get a pretty decent exact answer right here, can't I? The velocity per second. And if you want to turn it into a decimal, you can right there. But I'm good with that. One thing though, why is the velocity negative? Oh yeah, it's going down. Velocity has direction, doesn't it? All right, so you with me on everything from number 70? There's a lot there. You with me on this I did over here on the side because I forgot to write it on my paper for some unknown reason? We good? All righty. So, page 256, do 49 through 54, 63 through 72, and 87 through 92.